An event is a subset of the sample space. So in my previous examples, these are the random experiments, and so these are the sample space. So any subset of this sample space is going to be an event. Okay, so let us describe this. So this one is one subset. So this is an event. And so this is an event wherein the first customer agrees to buy the life insurance, but the succeeding customers did not agree to buy the life insurance. This one would be the event when either all the customers agreed to buy the life insurance or all of them did not agree to buy the life insurance. Here, this is the event when two of the three customers did not agree to buy the life insurance. And so this one is one event. This is the event when you chose to go to school wearing Nike shoes and white shirt. Okay, so the counting principle. So when we are talking about the sample space, it's not always convenient to list all the elements in the sample space. And you can see it from the tree diagram. And not only that, in statistics, what we are more concerned about is how many elements do you have in the sample space. It's not exactly in particular what are the particular elements of the sample space. In most cases, it's not practical to do it, especially when you are talking about experiments that will yield many outcomes. Instead, we are more concerned on the size of the sample space. When you say size, it means how many elements do you have in the sample space. And it's not always practical to list all the elements, like doing it through the tree diagram. And so I am introducing to you the counting principle. If an experiment has two stages, and the first stage has n sub 1 outcomes, and the second stage has n sub 2 outcomes, then the size n, okay, so you call it n, the size of the sample space or the number of elements in the sample space, and we call it n, is n sub 1 times n sub 2. And so if you have three phases or three stages in the experiments, and each phase has n sub 1 outcomes, the second phase has n sub 2 outcomes, the third phase has n sub 3 outcomes, and so the total number of outcomes is n sub 1 times n sub 2 times n sub 3. And that's going to be the size of your sample space. So in this experiment about tossing a coin and rolling a die, we saw that we had 12 outcomes. So the size of the sample space is 12. But we didn't have to always produce the tree diagram. It's not always convenient. What we can do is we can just use the counting principle. The first phase has two possible outcomes. It's 2. The second phase has 6 possible outcomes. And so the total number of outcomes for the entire experiment is 2 times 6, which is 12. And if you will count this one will count to 12. So let's go back to the experiment about choosing from among 3 pairs of shoes. And so you have 3 pairs of shoes and 5 pants, okay? White, blue, white, yellow, green, and red, and 6 shirts. Also a white shirt, a blue shirt, yellow shirt, green shirt, and red shirt. In how many ways can you go to school wearing shoes, pants, and shirt? So you will choose from among these the outfit when you go to school. So in how many ways can you go to school? So that is like, what is the size of the sample space? So you can do it using a tree diagram, but we can use it using the counting principle. Using the tree diagram, this is how you will do it. First, you have 3. You will choose 3 pairs of shoes. So this one stands for Nike, Puma, and New Balance. And then after that, you will choose from among the 5 pants. White pants, black, yellow, green, and red. Okay? And then you will have another branch of lines here. And that would stand for the shirts. Again, you will, for each of this point, you will have 6 branches. And so if you were to do the tree diagram, this is a lot of drawing to do, a lot of diagramming to do. And it's not convenient to do this. And so this is what we can do using the counting principle. The first phase of your experiment has 3 outcomes. The second has 5. The third has 6. So using the counting principle, or sometimes they call this the fundamental principle of counting, or the fundamental counting principle. The total number of possible outcomes in the entire experiment, which is the same as the size of the sample space, is 3 times 5 times 6. And that is equal to 90.